Hey guys, how's everybody doing today? My name's Corey, of course, you know that, and welcome back for part two of link analysis. This part two will actually consist of three separate videos that'll be roughly 20 minutes long. I want to make sure that we kind of get through a majority of this. Uh, Sorry in advance if my dog decides to bark, but I'm not going to go in school to record these, and he doesn't always listen. So, let's get on to it. So, let's do a quick review of Kleinberg Hits. Kleinberg Hits is a search algorithm that when you initially search, it's going to search for your content. And then it's going to bring back a whole bunch of web pages, all related to that content. Now, what's going to happen is it's going to calculate authority scores and hub scores for each and every website. Right? So you have a hub score and an authority score for both of them. And then it's say which of these websites are the best, and it's gonna order them according to authority and hub scores. The higher your score is, the closer to the top you are. All right. So now that's let's talk about a few things that are different in the next algorithm. Right. So PageRank. Right. So PageRank, what it initially does is it says, I don't care about the content. Every web page is going to have their own rank. Okay, so every web page has its own rank, and only one score instead of two. Whereas Kleinberg Hits, you have two scores. You have an authority score and a hub score. PageRank, no, you have a page score. That rank is for that web page. It doesn't care about whether you're an authority or a hub. You have a rank, one rank for your web page. Okay. And then after all the web pages are ranked, now Google goes back and they rank their pages once every 3 months or so. So that makes it a little bit easier on them, but the processing is can be expensive, right? Because think about that, 1 billion pages. We're going to talk about that later. Trying to rank 1 billion pages. So let's go ahead and get into this. So PageRank, it was developed by Larry Page and Sergey Brin at Stanford University, based on the idea of a random searcher. So basically, a person is on one page. They randomly go to other pages based off of some probability, right? And what is the probability that they would end up on a specific page based off of um, in degrees and out degrees. Okay. The page uses Markov chain states, so basically frozen state, and you follow the pass through. Okay. Probability of moving from one page to another page is modeled as a transition state probability, and we'll talk about that here in a minute. All right. So PageRank is really simple, right? So the rank of page is equal to the summation of the rank of pages and the out degree. Okay. So let's look at the rank of page Y. So we have page Y, we have page A, we have page M. Y has two out degrees, one going to itself, one going to A. A has two out degrees, one going to Y, one going to M. And then M has one out degree, which is just going to A. Okay. So now let's look at what the weights are attached to each of these pages. So we take the out degree, so that's 1, 2, okay? So all of the out degrees are going to be the rank of Y divided by 2, okay? Rank of Y divided by 2. That means that the summation of out degrees is totaled, the weight is totaled up to 1. So we have the rank of A going out, rank of A going out. That would be the rank of A, right? So the summation, it would come out to whatever A is, total of 1. All right. And then rank of M is just equal to the rank of M coming out. Okay. let's look at the functions. Rank of y is equal to the rank of y over 2, rank of y over 2, plus the rank of a over 2. So the rank of y it depends on itself, right? So we have rank of y is equal to the rank of y of 2 because it's pointing to itself. And then we have the rank of a pointing to y. These are the outlinks pointing to in degrees. So y is pointing to itself, a is pointing to it. Rank of a. So we look at rank of a. What is pointing to rank of a? Rank of y is pointing to rank of y over 2 is pointing to a, and rank of m is pointing to a. So the rank of a is equal to the rank of y over 2 plus the rank of m. Now, rank of m, what's pointing to it? Rank of m is equal to the rank of a pointing at it. Now these right here are real simple to solve, right? But think about it, this is only 3 web pages. And only 3 links, really, right? 1, 2, 3, 3 web pages. 1, 2, 3, 4, 5. 5 total in and out degrees. Okay, not a whole lot of issues, but this constraint right here, this constraint is what gives us a unique score. So let's go ahead and solve this real quick, right? So here's our solutions. So we have, let me bring this back over here so you guys can see it. Okay, so we have the rank of y is equal to the rank of y over 2 plus, and forgive my handwriting, I know it's horrible, but we make do. Okay, and then the rank of a, let me get this up here, is equal to the rank of y over 2 plus the rank of m, and then the rank of m is equal to the rank of a over 2. Now we could go through and set this up in a matrix, but substitution just works really well here. So we're going to take this right here. This is the rank of m is equal to the rank of a over 2. So we're just going to go ahead and put that right here. Right? So now we have this rank of a over 2 up here, which makes it easy. So I'm going to get rid of this real quick. Makes this easy to solve here. Okay, so let's solve for this so we can just plug it in. So we get RA is E minus this minus this is equal to this. Alright, so I messed that up. Let me fix that. I need these two swapped. Alright, it wouldn't really matter. We can solve it both ways. Alright, so RA over 2 is equal to RA minus RY over 2. So let's go ahead and take this out of here and plug that where that is. See, RA over 2, these are equivalent, so we can just go ahead and plug those in. Right, and then we can see that this and this cancel, so RY is equal to RA. Alright, so RY is equal to RA. Okay, now let's go back to that original equation here, and let's this, let's go to this equation right here. So we get ry plus ra plus rm sorry about that, guys. I just didn't want to recopy that. Is equal to 1. Right? So we know that ry is equal to ra. Okay, so let's go ahead and change out one of these. Right? So ry is equal to ra. Let's take that. Plug that in there. And then rm is equal to ra over 2. So let's go ahead and take that, plug that in there, and then over 2, right? So now we have 2ra plus ra over 2, which is 5 over 2 ra is equal to 1. Ra is equal to 2/5. Ry is equal to 2/5 because they're the same. And then we have Rm, which is equal to 1/5. Okay, so in essence, we solved that by hand pretty quickly. A computer could solve it in seconds. Okay, but imagine having to do this for a billion web pages. It get pretty quickly monotonous, right? So with PageRank, the rank is equal to the summation of the rank of the additions. These equations can be written in a column stochastic matrix. This column, let's call this column stochastic matrix M. The rank vector R is the eigenvector of M, or is an eigenvector of M. Since M is a column stochastic matrix, the largest eigenvalue is going to be 1. And R is unit length, and each column of M sums to 1. So MR is going to be less than or equal to 1. And we can solve this using a power iterative method. We talked about this before with Kleinberg hits. Because it uses the power iterative method with single value decomposition to solve for the eigenvectors. So let's look at this PageRank here. And so we're going right back to the same, this is the exact same matrix as before. Now, when we did the adjacency matrix for Kleinberg hits, we just use 1s and 0s, right? That doesn't help us a whole lot in this case because we want to keep this column stochastic, right? And we also did it by row instead of by column. So when we look at this, we're going to do this by column instead of by row. So we're going to say what is the weight of the degree from y to y. From y to y, so that's 1/2. What is the rank of the degree from y to a? So that's the 1. Only 1 comes from y to a, divided by the out degree, which is 2. Right? So, and then from y to m, 0. Okay. What about from a to y? Well, there's 1 that goes from a to y, and there's a total of 2 out degrees, so 1/2. From a to a, there's not 1. From a to m, there is 1, but the total out degree is 2, so we get 1/2. Great, and then we get 0 from M to M, or from M to Y, excuse me. From M to Y, there's no link. From M to A, there's 1, but there's only 1 out degree, so its whole weight is on that 1 out degree. And then from M to M, there's 0. So we can set this up in this matrix here. YAM is equal to, so R is equal to M dot R, right? So we get the matrix times the vector of ranks is equal to the rank. Okay, that gives us this here. The same, it's no different. So the PageRank power iteration, we're going to take the rank is equal to 1 over n, and then we're going to solve through, go back to 1. We're going to continue doing this. I believe it's 4 times. But here's the example, right? So we get ry is equal to 1, and then this is the initial rank that sorry about that cut. My dog decided he wanted to start getting antsy. Anyway, so this is the initial rank. We're going to take this initial rank here, and we're arbitrarily setting it to equal ranks for everybody. We're going to take that rank and we're going to do some matrix multiplication with the adjacency matrix, the column stochastic adjacency matrix. So let's take a look at what that looks like. So we have our adjacency matrix. We're going to multiply it by 1/3, 1/3, 1/3. So 1/3 times 1/2 plus 1/3 times 1/2 is 1/6 plus 1/6, which is 1/3. Then we're going to have 1/3 times 1/2, which is 1/6 times plus 1 times 1/3, which is 2/6, which is 3/6. All right, and then we're going to have 1/3 times 1/2, which is 1/6. That gives us this new rank vector. Now we take this new rank vector here, and we're going to multiply it by the same matrix again. Okay, so we get 1/3 times 1/2, which is 1/6, plus 1/2 times 3/6, which is 3/12. So we get 2/6 plus 3, or 2/12 plus 3/12, which is 5/12. And I'm sure you guys can do the rest, but as you can see, eventually it gets down to 6/15, 6/15, and 3/15. This is after so many iterations in this power method. I think right here is a good time to stop this video for a small break and then come back for part 2, please. All right, I'll see you guys shortly. Bye.